As far as gas stoichiometry is concerned, it's just calculations that we've already been doing. We're just going to substitute a volume-volume ratio for a mole-mole ratio in the regular railroad tracks. And we're going to do mostly practice exercises in class for that. I've assigned some on the annotated schedule that I gave you. But there's a couple things in these notes that I want to go over that you haven't seen before that aren't going to look familiar. The first of these is a density calculation from the ideal gas law. Density, remember, is mass divided by volume. So if we take PIVNERT, the ideal gas law, and we solve it for volume, and we put that into the density equation, we get that density is equal to, on the top, pressure times the mass, we still have mass from the original density equation, divided by nRT, moles, R, and temperature. Now, we can separate out the mass over moles. That's grams per mole. That's molar mass. So I'm going to replace the m over n and replace that with a capital M for the molar mass. So an equation for density is pressure in atmospheres times the molar mass, grams per mole, divided by R, liter atmosphere per mole Kelvin, and temperature in Kelvin. So the higher the pressure, the higher the density. And that makes sense. We're squeezing more particles into a smaller space, right? The higher pressure, so the density is going to go up. The higher the molar mass, the higher the density, because molar mass is, well, mass. The more molar mass you have, the higher the molar mass, the higher the density is going to be. The higher the temperature, if everything else stays the same, the lower the density. So if we raise the temperature of something, but we have the same pressure, it's going to expand to keep the same pressure, which means they're farther apart, they're more spread out, it's occupying more volume, it's going to have a lower density. This is Charles' law. This is how hot air balloons work. When you raise the temperature, you lower the density of the gas inside the balloon, and lower density, of course, rises through the higher density gas to float up higher, and you can float in a hot air balloon. So for this sample problem, and I want you to try this before you come to class tomorrow, use that equation we just looked at to find the density of carbon tetrachloride vapor. So carbon tetrachloride is CCl4, carbon tetrachloride, 4 chlorines. The vapor is at 714 torr, change that to atmospheres. 125 degrees Celsius, change that to Kelvin. So the pressure we've got in atmospheres, find the molar mass of CCl4, divided by R, the one we've been using, 0.08206, divided by the temperature in Kelvin. That will give you your density. This problem is exactly what you did in the lab. They take a large flask, they completely emptied it out, completely empty. The flask weighs 134.567, fill it with the gas, and it weighs now 137.456. We've got a pressure, we've got a temperature, we've got a mass of the gas, and just subtract the empty flask from the now full one. Fill it with water to find out the exact volume. And now we've got PIVNERT. We can find the molar mass. This is the exact same calculations in the lab. Give this one a try. We'll go over it in class tomorrow.